I'm very pleased to be introducing Dr. Linda Mearns, who has too many titles to tell you all about, but I'll just say she's a senior scientist at the National Center for Atmospheric Research in Boulder. And something that you might not know about her is that she actually first studied philosophy. Now she's an atmospheric scientist. So take it away.
Okay, great. Thanks for that cheery introduction. And let me say I'm very glad to be here. I've never been to Ontario before, and or to London specifically. And so I did study philosophy, but I focused on medieval linguistic philosophy and French existentialism. So not a lot of philosophy of science, but I've caught up with my philosophy of science pals in various contexts. So one of the things I really focus on is uncertainty, and I'm actually very fond of uncertainty in a sense. Of course, many people have quotes about uncertainty. My favorite is Voltaire, because I think it's the most, dare I say, accurate, using the term casually. Doubt is not a pleasant condition, but certainty is an absurd one. And I'll tell you one other thing, using up more of my precious time, that one of the things I look at is integrated uncertainty in climate change research. And we had a very nice 2.5-week colloquium this past summer at NCAR, and 4 of the people who were involved in that colloquium are here today. So I can't resist to give a little real up-close example of uncertainty. So Rob Lempert is back there. You'll be hearing from him later. And I were talking about just, London, Ontario, and we had each gotten different estimates of the population of London, Ontario from our various drivers. And I got a figure of about 300,000. Rob got a figure of about 400,000. And we had a very high-level discussion about whether or not we should average those two values to come up with the best estimate, or provide the range of somewhere between 300 and 400. So that sort of set me up a bit for this talk. Now, this talk is going to be, shall we say, quite different from the talk we just heard. And I'm going to talk about some things that the previous speaker discussed, but I'm going to be talking about it from a very real, up-close climate model kind of way, and that is about how can we best evaluate the quality of climate models on regional scales and establish their credibility, and why should we care about this. One other thing I should mention, that my biggest concern about uncertainty today is actually my uncertainty about how this talk is going to come off, because I've included some very new material that I haven't really thought about very carefully. So I'll be very interested in your reactions, and my own, for that matter. Okay, so why are we concerned about reliability and credibility? Because for a number of different reasons. For recommending what climate scenarios should be used for impacts assessments and resource management decision making. And this remains, everybody sort of has their favorite stakeholder at this point. Everybody works with people who are trying to use climate model results in something closer to decision making, or at least, let's say, adaptation planning. And there remains a tremendous amount of confusion and variability and uncertainty about what should be used at different spatial and temporal scales. Another purpose for looking at this is for selecting which global models should be used to drive regional climate models. And since this talk is about regional climate models, this is particularly opposite to what I'm going to be talking about. And then, of course, for differential weighting of climate model simulations to provide better measures of uncertainty, probabilistic methods, and that sort of feeds back to the first purpose. And there's probably a, yes, great, got it. And as I said, I'm mainly going to be talking about this in terms of multi-model ensembles, and mainly from a regional climate model point of view, which reminds me, so I don't know a lot of your backgrounds, aside from the people I know. So how many of you are basically familiar with what a climate model is and what a climate model ensemble is? Okay, good. Chance to skip slides. All right, so since I'm already far behind. So the climate model system, I won't go through all this. There are a lot of different components. It's delightfully complex. And climate models obviously try to simulate the major or many of the major processes that refer to the real climate system. Another important series of terms I'm going to use, but never define very carefully, is what do we mean by these terms reliability, confidence, and credibility? And again, I'm using these terms in a climate modeler's world. For a long time, these terms tended to really mean something pretty simple and straightforward. If a model reproduces observations well, whatever well means, whatever observations we're talking, then we should have confidence in future projections based on this model. But I'd like to argue that that's woefully inadequate, and I'm not the only one who thinks so. So the relationship to uncertainty, the confirmation and so forth, and the idea of a climate model ensemble is that there are different climate models. They tend to respond differently to climate forcings, such as increased greenhouse gases. The standard way of approaching this has been the one model, one vote approach that has been articulated by many, including several papers by my esteemed colleague, Reto Knuti. Wave to the people, yes. And one of the issues is, well, does this really make sense given differences in model performance? And there's been a very active research effort in the past 8 to 10 years to come up with different ways of evaluating models for the sake of getting away from the one vote, one model approach. And I still think we don't know really what the most appropriate methods are for this for different purposes. All right, so this is just an overview telling you that indeed this is an ensemble of climate models, in this case from the most recent, set of climate models run for the CMIP-5, the Climate Model Intercomparison Project number 5, which was used in the most recent IPCC report. And let's just take one of these scenarios of future greenhouse gases, and you come up with this kind of envelope, this plume. Why do you come up with this plume? And this is for a very coarse resolution phenomenon, which is just global temperature. And this is the point that different models respond differently to the same forcings. So I'm going to go through very quickly some of the examples of credibility analysis that's been done for global climate models, and then talk about the greater complexity of trying to do this with regional climate models and why we deal with regional climate models at all. So one of the first efforts to come up with differential weighting of climate models was by Georgi and Mearns. That's me. And we tried to come up with, so this is way back in 2019, well, not that bad, 2002, 2003, and we're trying to figure out, well, how would you differentially weight models? I mean, everybody publishes articles and they say, well, our model validated really well, so we should have confidence in this model. But everybody is doing this, and everybody is pretty much saying the same thing. So we decided to really come up with this concept of the reliability, a reliability criteria, which involved the performance of the global models, AOGCMs, as well as model convergence. And convergence, I mean, is the relative closeness, let's say, for temperature of the different simulations. Now, the reason why I'm going through this is because really it is one of the earliest attempts to formalize differential weighting, but also it's because of the reaction of the climate community to this paper. It got a lot of, very useful criticism. But what was particularly interesting to me was the fact that what people said they disagreed with about this method was very different from what they actually did. And this particularly had to do with the model convergence, that having models agree on a change of some sort is no reason to give them greater weight. But in point of fact, you'll see all over the place that when models agree, and yes, we all say yes, but they have to agree for the right reason, and of course there could be, let's call them sort of errors compensating errors that result in a good simulation or whatever. But the reality is, for example, if you've looked at the IPCC, that models agreement for a very long time really mattered and is considered a positive good, assuming that it's not for the wrong reasons. But when we presented any of this work, people would object very strongly to the model agreement criterion. And I'm still interested about the difference between what people say and what they do. Of course, that's not the first case in human history where there was a contrast in that regard. I'm just surprised to find it to be the case around climate modeling. I'm going to skip that detail. So what we found was, and by the way, I'll go back to this for a sec. We did this on these are global models, but we did it for a bunch of different regions throughout the world. And I'm not going to try to go through that diagram. But that we did find that by using the REA methods compared to just a simple averaging, that, yeah, there were some differences in the values of change in temperature from a few tenths to 1 degree centigrade for temperature, and from a few tenths to 10% for precipitation. We also stated that the uncertainty range is narrower in the REA method, and we also found that the overall reliability from the model performance was lower than that from the model convergence, and therefore to improve reliability, you must reduce model biases. Now, this raises another issue about the whole concept of reducing uncertainty. Is that an important thing for climate modelers or people who use climate models to do? And is that why we're improving the models all the time and so on and so forth? There are a lot of important differences in this. Different positions that people can take. And I maintain that in many, many cases, the drive to reduce uncertainty is an ill-formed goal. And I may or may not get back to that. OK, so there has been, and particularly in 2008, there was a tremendous research surge on looking for the correct performance metrics for climate models. Climate models are complicated. They have a lot of different variables. What are you going to evaluate in what spatial and temporal scales? And Peter Gleckler put out one of the very important papers on this in 2008 and emphasized the importance of evaluating a broad spectrum of climate processes and phenomena. And he came up with many, many different metrics. But in the final analysis, and this was all looking at the CMIP3 data, the different climate simulations that were used for the 4th assessment report of the IPCC, after all his work was back in 2008, it remains largely unknown what aspects of observed climate must be simulated well to make reliable predictions about future climate. Now, one can really pick that sentence apart in terms of what do half of these words mean? But in the climate world, perhaps more than in the world of philosophy of science, these things are not picked out very carefully. Now, so again, the 2008 John Walsh did a very nice study, also looking at the same set of models. And this is what's interesting about all of this work. They were all looking at this CMIP3 ensemble. And so John looked at the root mean square areas of seasonal cycles of temperature, precip, and sea level pressure in Alaska and Greenland, and found the tendency of models with smaller errors to simulate a larger greenhouse gas warming over the Arctic and greater increases in precipitation. And this became one of the very important things to do, is to establish a relationship between biases and the climate change response. Because if you have that relationship, you can dig into the processes and say, the models that are better have a different climate change signal, and we can actually believe that more. And he actually said that the choice of the subset of models may narrow uncertainty, again this drive, and obtain more robust estimates of future climate change in the Arctic. And again, this is an issue of, it's assumed in this article that narrowing uncertainty is a positive good for many, many reasons. But it's often said it's a positive good for the sake of the use of these simulations and scenarios for actual decision making. Another example, and I'm going to go through these really quickly, is a paper by Francina Dominguez and colleagues, and I'm bringing this up because I'm going to talk about the Southwest later. And again, she came up with some nice criterion, also using the CMIP3 models, used a modified REA method, as well as an additional variable about reflecting the location of the subtropical jet stream. And they actually, from all of the CMIP3 models, they came up with 2 models that they felt really worked well. And they wanted to use these 2 models, in point of fact, to drive regional climate models. And she's at the University of Arizona, and they have a lot of stakeholders there who are concerned about things like water resources in the future, extreme heat, and other factors. Now, remember this model, the Hadley Center Climate Model version 3. It was a major modeling center in Great Britain. Remember that model, it's going to return. And I'm going to skip those things. So those studies I showed you were cases where a difference based on sub-selecting models was established. One region here, one region there. But there are a bunch of studies where subsetting made no difference. So for example, a paper by Pierce et al., again for a different region, the western US, used 14 randomly selective GCMs, produced results indistinguishable from those produced by subset of best models. All right? Reto Knuti et al., a major article, metric of precipitation trend, they looked at 11 randomly selected GCMs, produced same results as those from 11 best GCMs. So you can say that by now, in 2010, we're seeing mixed results. Some areas it matters, some areas it doesn't. Now, this paper is by a good colleague of mine. This is Brecky et al., 2008. What's interesting about this paper, again, dealing with the same set of climate models, but his interest was really in terms of coming up with different criterion based on the different use. And this is from Northern California. And they actually came up with different criteria based on whether or not you were concerned about water supply, hydropower, or flood control. This is very interesting because it's really keying what you're subsetting the models based on the actual user needs, but combined also with obvious consideration of climate processes. And there was some effect, not so much on temperature, but here's a PDF of precipitation, but it wasn't that strong. But it was a very interesting attempt, I think, to cull these models based on different criteria for 3 different management contexts. And what they would do is they would actually eliminate models that didn't reach certain performance criteria. So I'd call that sort of a mixed result. I hope I get to regional models soon. Great anticipation on my part. Okay, so selecting weighting of regional climate models. Now, this is the main event. And this is very much related to an issue about regional models, the added value issue, which is another one of these contentious issues that just hangs out in the climate modeling community for decades. And as a matter of fact, I'm actually working with Lisa Lloyd, a philosopher of science, on a paper about this whole concept of added value from a philosophy science point of view. All right, so first of all, how does the regional climate modeling business work? As many of you know, I'm sure that climate models are run at different resolutions. A typical resolution now, this is pretty coarse at 400 kilometers, but like maybe at 150 kilometers for the CMIP-5, the most recent set, many of them. And this is what the topography of the US looks like at 150. It's still kind of vague, shall we say. And then we get down to regional models. Here we are. The topography at 25 kilometers really stands out. 10 kilometers, even more so. And of course, now regional models are being run down to a single kilometer, and even finer in point of fact. Now, a side issue I'll dare to bring out is in one of the earlier US climate assessments back in 2000, 2001, when models really were running at this resolution, a lot of the users, when we talked to them, and this was this effort to include users, real people, not just climate scientists in the National Climate Assessment. Yes, that sort of makes it sound like climate scientists are not real people. That's not exactly what I meant to say, but oh well. And when we showed them results on the actual resolution of this, they just threw up their hands and walked away. Why? Because this portrayal of the topography does not tell them that this is their region. They do not recognize that as their region. And if you don't have that perceptual connection, it's very difficult to get people to take the results seriously, no matter how completely you validate it. And that's an interesting point about working with users. So the assumption is, and this is often true but not always, that with higher resolution you resolve more small-scale processes. Obviously, you better resolve the topography, so the effect of topography on air masses and so forth is much better represented. So the basic regional modeling strategy is that you use boundary conditions from the global model, and it provides initial conditions, and then the lateral meteorological conditions, usually every 6 to 8 hours, temperature, pressure, humidity. And that the global model is providing a reasonable representation of the large-scale response to forcing on the order of hundreds of kilometers. And then you rely on the regional model that's embedded and driven by this, provides finer scale on the order of tens of kilometers response. So the trick is, so then the simulations rely both on the quality of both the global and regional climate models, which just makes the whole issue of confirmation or credibility of whatever you want to call it at least twice as difficult, and probably it's a very nonlinear phenomenon. All right, so this shows you, this is a bit of an old slide, but still it's one of the models that we used. So it's got a resolution of about 280 kilometers. It's North America, obviously, with much rougher topography. And a higher resolution model at 50 kilometers looks much more real. Also, when I first saw this and I thought, oh, what is that? It looks like Florida has escaped from North America. Interesting choice for a scenario. It turns out, of course, that's not true, that this is supposed to represent the Caribbean, but it's an interesting choice to include the Caribbean but not Florida. And I can't really speak for what the Hadley people were thinking when they did that. At any rate, so with a higher resolution, obviously you get Florida. That's very nice. And things look a lot better. And this 50-kilometer resolution is important resolution. for what I'm going to be talking about very soon. So as I said, there's the problem of the credibility of two different types of models and their simulations. And I want to say something about this added value. So the added value is basically, do you really get more useful information using this embedded regional climate model than from the global model? And this has been a bone of contention for a very long time, and it partially depends upon this definition of added value. So IPCC definition in the most recent reports, it's the measure of the extent to which the downscaled climate is closer to observations than the model from which the boundary conditions were obtained. I think that's a very restricted definition. And really, in most cases, you can say, well, of course it's going to do better. It's higher resolution. That's not always the case, but it's very often the case. We've expanded on that to really just say that it's additional knowledge about the climate gained from applying an RCM or other downscaling method. And I would say that the IPCC definition is necessary but not sufficient. Now, I'm going to give you a quick example of the major effort that was made to metrosize results of an ensemble of regional climate models. And this is from this major project for Europe, in which a number, I think 15 different regional models were nested in a number of different global models. And they came up with 6 different metrics. And these are, you know, reasonable metrics for a lot of these things, to look at the large scale, the mesoscale signal of temperature and precip. They also looked at PDFs, extremes, and so on and so forth. And the way in which they combined this, their major way, was to make it a product of all of these metrics, so that the models had to do pretty well on all of them to be considered useful, shall we say. So here is the overarching result for Europe. This is from Jens Christensen's paper, 2010. And a lot of work was put into doing this. And you actually do get, let's just look at they looked at different ways of combining the metrics as well. Let's just look at the product one, which is their main one. And here are all the regional models. And we have one, shall we say, tall poppy. This happens to be the ROCMO model from KNMI. Clearly beats out all the other models by quite a bit. The strange thing is that if you actually read the article, not much is made of this. And you would think, God, the KNMI people, we've got the best model in the world, talking about best models. But they found that when they combined all of this to create probability density functions, distributions, for temperature and precip, that the weighting, when they weighted things by these factors, really didn't end up making that much of a difference. I think it's a great attempt. It's very interesting, and we actually used it in a project that I'm going to tell you about very soon. How am I doing on time?
You have about 3 minutes till your 30-minute.
That's really bad.
Yeah.
That's extremely bad. All right.
You have 18 minutes. How's that? Does that sound better?
Yeah, yes and no. Okay, now, the main event is for me to talk about these 2 studies that we've done with this program that I've run, which is the North American Climate Change Assessment Program. And we're also looking at different uncertainties, both the global and regional models, which is what everybody does. We've created a bunch of multiple high-resolution regional climate scenarios for use and impacts and adaptation assessments. Note, I'm saying assessments, not actual planning purposes or actual adaptation implementation. Had a lot of participants, various funding, and here's the domain. And everything was done at 50 kilometers. And I want you to focus on 2 areas. Think about 2 areas. The northeast, and then again this southwest. And I'm going to have to run through this pretty quickly, but I think I can get you the basic messages. So as typical of regional climate modeling programs, you do one set of simulations using what you would call the best or observed boundary conditions, and this presumably tells you what the best simulate, how well the model can simulate the climate under more or less ideal conditions. And then you drive the models with the global climate models. In this case, we did the current and the future as two different time slices. And here's the four models we used: the global models, GFDL, Canadian, the Hadley, and the NCAR CCSM3. And here are 6 different regional models that we use. So all of these models respond differently to forcing, all right? And we did a very nice matrix design. The red X's show the simulations we did, such that every global model provided boundary conditions for 3 different regional models, and each regional model used 2 different global models. And it's still the only experiment that has actually used a balanced factorial design. As a matter of fact, to use any kind of statistical design at all, which is interesting to me, because Europe, for example, has done a lot more work than we have. So that's just showing that. All right, so here we are. Actually, I'm going to skip that. So just to say, we also use those same weighting factors as the ensembles, and here are the results for our 6 models. And I'm not going to go into that, except that we also have, well, I will mention that, including the large-scale factor, the best model, if you wanted to base it on this, is the Canadian regional climate model. How great is that? And we didn't know that when we started. And what we find from the IPCC is that there's high confidence that downscaling adds value both in regions with highly variable topography, i.e. mountains, and for various small-scale phenomena, such as coastlines. So that's a nice thing, a big message from the IPCC in the summary for policymakers, I think. Okay. Where are we now? Well, also from the IPCC, still no universal strategy for weighting the projections from different models based on their historical performance. And the question is, why would one expect there to be? And one of the whole points is that different phenomena dominate in different regions, and that's one of the reasons why climate is so complicated. So more process-oriented approaches. So I'm going to go through just this main one slide that's kind of wordy, but this is the approach we took in looking at some regions within the NARCCAP simulations. So so this is really about establishing process-level differential credibility of regional scale climate simulations. I should probably turn that into an acronym, and it would go a lot faster. All right. Determining through in-depth process-level analysis of climate simulations of current or past climate, the ability of the model to reproduce those aspects of the climate system most responsible for the particular regional climate, then analyzing the model response to future forcing and determining specifically how the model errors actually, in the current simulation, affect the model's response to the future forcing. And this is really coming down to what models' errors really matter. And I think many people certainly agree with me that this is what ought to be done. One of the reasons why it's not done more often is that it takes a great deal of time. And one of my concerns about climate modeling is that before we're finished really looking at all the outputs from the last collection of models, we're moving forward to the next collection, and we also always assume that the next collection is inherently better, and we really don't know that, and that's a very dangerous assumption. Oh, bad, bad, bad. All right, so my basic message is we looked at 2 different regions, the North American monsoon and the Northeast, both for summer precipitation. And I'm really going to have to rush through this because I do want to see if there are any questions. Anybody planning to ask a question? Oh, all right, 2 heavy hitters there. All right. all the more reason to race through this. So, Melissa Bukowski, young scientist in my group, did an absolute excellent job leading this paper and went through a great deal of analysis. I'll just share a couple of these. One of the big contrasts I'm going to make is with the models that were driven by the CCSM, that's the NCAR model, and those driven by the Hadley Center. So with the NCAR model, this is just the seasonal precipitation. The black one is the regional. Forget that, the gray one. These are the results for the 3 models driven by the CCSM. And none of them are capable of getting the seasonal cycle of the monsoon. I mean, complete miss, no chance. Hadley Center. We only had 2 results for this. Sure, the MM5 Hadley model, the MM5 regional model, it's an exaggerated monsoon, but it basically gets the basic seasonal structure. And so one of the issues is, well, how important is this bias versus the fact that it basically gets the monsoon? And then the Hadley regional model in that model, in the global model, does the best. So I'm not going to torture you with all these precipitation changes. I am going to show you that one of the things we did, we got a very nice relationship with bias and the precipitation change. And this is the kind of thing you really want to see, where the bigger the bias, the bigger was the decrease in precipitation. The smaller the bias, the smaller was the change in precipitation. And I think there's been very few, if any, good relations like this for precipitation shown. All right, this is a whole other story about the subtropical high. I'm not going to have time to go into it. Let me just say that the CCS German projections really do not nail the subtropical high, which has another effect on precipitation at all. Does a very poor job of locating the high and establishing the strength. All right, so here's a map showing all the different factors we looked at, and I just want to point out one thing. So here is the MM5 CCSM, the poorest model, absolutely. Barely got anything right in what we carefully considered. Versus, of course, the HAD-RM3, HAD-CM, got all of them correct. An amazing contrast that we really weren't necessarily going to expect. Time?
Oh, you're good. You have about 7 minutes.
Oh, wow, plenty of time. So I'm not going to go into it, but the CCSM-driven RCMs produce climate changes that are not credible. Had we known the quality of the CCSM in this area, we probably wouldn't have used it. And the HAD-CM was really a great simulation. One point about the increasing resolution. So Melissa did a simulation with, at higher resolution, 10 kilometers, and needless to say, if the boundary conditions are fatally flawed, higher resolution is not necessarily going to lead to a better simulation. As a matter of fact, it provides you a great deal of detail for a very poor simulation. So, no, but this is important, because you'll hear people say all the time, higher resolution is better, and it just is not always. All right, summer precipitation in the Northeast. I don't have time to go through this. Different set of criteria used by Jean Thibault and Angie Seth. They also did process level results. They chose 4 quote-unquote best models with different changes in precip, although they were all small. The bottom line is that I want to get to is that the best of the NARCCAP model combinations for the Northeast summer is the worst for the North American model precipitation. So the best in the Northeast does absolutely terrible in the Southwest. And this is true for 2 of the other ones that were rated highly there, had a very low score also. And only 1 model combination results was somewhat credible for both regions. And so the point is, what does this mean? You know, I say, well, we wouldn't have used CCSM if you'd known how bad it was in the Southeast. Oh, really? But if you're doing a modeling exercise over all of North America, what do? Do you go through every single region and make sure that the global model works well? An important limitation of NARCCAP was that the driving GCMs were not chosen based on their performance over North America. As a matter of fact, they were chosen mainly for pragmatic and political reasons, to be frank. And they don't span the climate sensitivity of whole suite of CMIP3 models. So certainly, even the best model is not really going to give you the kind of uncertainty about future climate change on a regional scale. So what do we need to make further progress? So what I used to say, until I actually looked at these results 2 days ago, I used to say, well, we all need many more in-depth process-oriented studies that examine plausibility of process change under future fortune, what errors really matter and which don't. But here we have 2 very good in-depth process studies that come up with very different results for different regions of the domain. Yikes. This is the only time I've used yikes as my conclusion for a talk. I hope it doesn't happen too many more times. I could say a bit more about what I think about this, but it's really very problematic. When you have such oppositional results for 2 different regions that are in essentially the same country. And I'm always worried about the danger of false uncertainty, and these are my very pathetic polar bears. Thank you.
Questions, or do you want to field them, or do you want me to pick people?
I'm happy to have you pick people.
Okay. Questions?
Yes, a quick question. I find it fascinating. I agree with most of it. I'm also working with a...
That's good. I don't know if I agree with any of it.
Heavily centered around a global climate model, and I'm using a regional climate model to downscale Jeddah, Hudson Bay lowlands up in the far north.
Yes.
But, and we also, as a means of validation, are comparing with the same reanalysis with the NAR data. And at the beginning of your speech, you said that the validation of the model in the past doesn't necessarily mean any adequacy in future projections, that this whole approach
it doesn't necessarily.
What alternatives would you suggest?
Oh, well, I still think really digging into the process level, what's really going on in the model.
That would be speaking of model diagnostics.
Well, when I talk about them, I'm talking about, you take diagnostics, presumably you kind of turn them into metrics, and away you go. Since I ran out of time, in point of fact, what we did was really an expert judgment. And we spent a great deal of time discussing what was important. We made a big assumption, really, should all those factors have equal weight, right? Is it just as important that the precip intensity is correct as whether or not they get the low-level jet going up the Gulf of California? I'd say it's much more important that it has the low-level jet than whether or not the precip intensity is correct. But somebody else, my friend Drecke, for example, might disagree with me from the point of view of flood control. So what you say called diagnostics, I guess, yes, that's probably similar to what I talk about real deep process orientation work. I still think that's very important. I'm just, quite frankly, a little blown away by how different the results are for the Northeast versus the Southwest. Because then let's say you're trying to develop national climate scenarios, because the next national climate assessment is coming down the pike, as it will in the States. I just think we don't know.
And there I see actually a fundamental problem, that if we do these diagnostics and we see that, for instance, there is an anomaly or a bias which might hint to a hidden process.
Right.
That actually, to me, is a big contradiction, because if the model actually misses this process in its parameterization, how can we use the same model to make future predictions? That clearly shows ourselves that we haven't understood the process.
That's right. That's right. That's the other thing, how well we understand the processes that are parameterized in the model. I mean, the problems are legion. My effort is to not get up in front of people and say we know nothing. Because that's not true. Oh, Gavin. See, I will call.
Okay.
Do you want to call somebody else?
I was going to say Lenny, Gavin. So Lenny, you're up.
Oh, you. God, between the devil and the deep blue sea. Sure.
Well, as a Floridian, where you sort of froze how far into the deep blue sea. I guess the issue here is just to point out that in that situation, you'd be driving the regional climate model points, land points, with inputs which were from a large-scale model, ocean points. There's something about inconsistency. You would have Florida in the GC in the
Oh yes, Florida's the great example.
But
yes.
the points you're driving the high resolution model correspond to ocean in the model that are actually driving.
Absolutely.
Which is a nice way to lead into my question, which is, so how do you stop?
Sorry?
So I would ask a question. Normally, I hadn't had such a good example of water and land.
Yes.
But if you're looking at upward infrared in the high resolution model integrated over a low resolution model grid box, and that difference is twice the forcing you expect from CO2, then isn't there a sense in which you just like to stop and hide the results from decision makers? And they may be useful for science, but it's the question of internal consistency tests. You start to fail to meet the
Come on, Lenny, you know me.
doing
I
things.
hide nothing.
What?
I hide nothing from
Well, in that case, stop the model is not running.
No, I mean, certainly this was a research experiment. And it's been used for impact research papers, all right? I have never gone and said, all right, you guys in California, you should really use these results to really develop and implement, to develop an adaptation plan and to implement it. All sorts of climate model results have been used to develop an adaptation plan.
What I'm suggesting is that they're very useful. It's very useful to have tests of when the results of a wide variety of different experiments can actually be useful in more than learning about the models.
Yes,
and so,
I agree.
So for things like in extrapolation, how far into the future can you get the southwest of constant horrible and still expect, on physical grounds, to get the northeast of the continent okay? I mean, are there ways to sort of work out our models may or may not be useful up to this sort of point, but after that we realize, just by looking at the internal interactions between the bits and pieces, that it really doesn't make sense to try and extract quantitative information from those models.
Well, that's why my final word is yikes. Because what relationship is there to, you know, what's going on in the Northeast and the Southwest? I mean, one of the interesting problems about a lot of these regional studies is that they only look at one region. And luckily we had this NOAA map project with the people at the University of Connecticut. And literally we just found out these results like 3 days ago and I was stunned. So I'm rethinking.
So, Mike, I know that you've thought about this, but the...
Sorry?
Sorry, I know that you've thought about what I'm just about to say, but I think it's worth...
Repeating, sure.
Well, I'm going to. So the question that a lot of people ask is, you know, is there added value in skillful, in predictions, right? So it's very clear that if you take a regional climate model that has better resolution than the parent GCM, you get, especially over topography, much better estimates of rainfall patterns and things like that, particularly over topography. It is almost never tested whether the predictions from the GCM-RCM combo are actually even different to the predictions of the GCM just extrapolated down to the station level.
Oh, you mean like with interpolation?
Yeah. I mean, however,
oh yeah, that's a big problem.
Right, and so the question that one should be asking in terms of added value is there a difference in prediction? If there is a difference in prediction, how can you evaluate whether that difference in prediction is actually increasing the skill or not? And it seemed to me with the NARCCAP experimental design that you didn't actually have enough information to test that with respect to variability over the period that you ran the GCM-RCM combo in the hindcasts. You could be looking at impacts of ENSO, you could be looking at impacts of Pinatubo, you could be looking at the long-term trends over that period, comparing it directly to the station data, and then saying, here is a objective, relatively objective, sense in which the GCM-RCM combo has better and higher skill in prediction of variance than the
And
GCM.
we've certainly done some of that, and you can look at Mearns et al. 2013 climate change letters to show some interesting work about intensification of precipitation decrease, which seems plausible from the intensification of atmosphere surface coupling. I think I'd actually pull out, I mean, one of the problems is that, of course, now, well, when do we stop in terms of resolution? And a good example is that a study by Lizzie Kendon et al. At the Hadley Center, in which they went down to, I think, like a kilometer, was it? Even less. And they were looking at the diurnal cycle of precipitation, comparing it to, I think it was the 10-kilometer simulation. And they came up with this amazing difference in what happened on the diurnal cycle. I can't remember the details, at 1 kilometer versus 10. And at the end of the paper, they say, based on these results, we believe if you're going to look at climate change and you're concerned about precipitation extremes, you have to work at this resolution. They have very good process arguments for why that diurnal cycle changes the way it does. But that's quite a leap to go that now everything should be done at that resolution. And I'm not saying that Lizzie was saying that exactly. I mean, it's also nice to have a nice little island like Great Britain that from an adaptation point you can think of as being somewhat isolated. But to me, you learn that, and we understand process-wise that this happens, so we don't necessarily have to do everything at that resolution because we understand it and we can make corrections in the closer resolution. I'm very concerned about going down to a resolution the size of my large toenail on my left foot.
I've seen that toenail.
Yes, you don't want to go there. Because, quite frankly, I look at the problem in a larger sense. Really? Will putting all that money into that effort, will that really solve the climate change problem? I doubt it. And we'll hear more about that from certainly Rob Lempert, I think. There's a lot of work that has never been done on vulnerability. I mean, and I realize I've got to stop at some time, probably very soon. Oh, when I'm ready. Well, okay.
Yeah, so I'm a philosopher of science, and I only know a little bit about climate science. So I wanted to make sure I understood the yikes at the end, and then if I do understand it correctly, maybe float a suggestion. So the reason for the yikes was we were looking at a variety of different regional models, and models that worked well with certain kinds of phenomena in one part of the US were completely different from the models that were working well with other phenomena in other parts of the US.
Correct.
Okay. So the suggestion I wanted to float is that this maybe isn't necessarily so scary or so worrisome because of this idea.
Easy for you to say.
Well, so this is the suggestion. That this notion of adequacy for purpose could really help sort things out here. So this was mentioned a bit in the last talk, but I know Ron Geary and Wendy Parker have written a lot about this, Parker especially in climate science, where the idea is that different models, we care about them for different purposes. So we could say, in the Southwest, what we want are models that are good for getting the hydrology right in a way that can help inform water policy in the Southwest. And in the Northeast of the US, we don't care about that so much.
But that's not true. We do care about that for the Northeast. Why would you say, I mean, you know, this adequacy for a purpose, but the fact of the matter is, let's say, for example, one of the purposes would be, we need a unified adaptation plan for the United States.
Do we need a unified plan or a coordinated plan?
That's a very good question. Maybe we don't need a unified plan. Coordinated might be good enough. But I think what was disturbing, not that it was different, that they were so starkly different. I didn't expect the same models exactly, but it was so different. I just was really, we were all taken by surprise. And I don't think the adequacy for purpose argument works here because there are resource concerns for water everywhere. And they're not necessarily stronger in the Southwest than the Northeast. It's more dramatic in the Southwest, but it's still there in the Northeast as well. That would be my opinion.
This is a small follow-up to, but rather than looking at the purposes to see this clash of how the models perform as a resource for getting deeper understanding about how the different pieces connect.
That's right.
And that seems to be a wonderful new piece of evidence that you can bring to bear and work on to deepen the understanding of how these things work.
No, I agree, and I appreciate that comment. I just literally have not had time to think about that enough. So, I mean, it's really, well, it's kind of interesting. This discussion has been very useful for me, actually. Because I was really worried about presenting this, sort of, talking about letting this happy group know exactly where we are. But I trust you guys, obviously.
We have about 2 minutes left, so if anyone has a quick follow-up.
I mean, I guess the really interesting question about whether this adequacy for purpose response is going to work doesn't seem to me to have to do with whether you want a unified or a coordinated plan. It has to do with to what extent you think these phenomena are causally independent, right? I mean, how much does the failure to get one region, is it plausible to think you can get that region so wrong and not have the match over here just be a coincidence rather than something actually projectable? I mean, how well do we understand that sort of question?
No, and I think that's something that we should really do more work on, absolutely. I'll tell you one very small anecdote. That with the NCEP-driven runs, when we submitted that paper, the Hadley regional model did horribly. It had this amazing bias in the central plains of being way, way too hot. Such that one of the reviewers said, well, you should simply throw that model out. This model ain't good for nothing. And it ends up being the best by a lot for the Southwest. So, I don't think we have a good answer for that, but I think it's another thing that this work can point to. What are the regional connections?
I think that's the real source of the yikes. Yeah. That we think there is a causal connection, then seeing that kind of, at some time scale, we expect there to be some sort of causal connection. So it's weird. All right. I helped myself to the last little comment there. All right. Time to wrap up and have lunch, so let's thank our speakers.